Hi, this video is on buoyancy, and it relates to the third section of Young and Freedman's University Physics of Chapter 14, which is on fluid mechanics. And so we've reached that discussion of fluid that comes to buoyancy. But this is pretty everyday stuff. In fact, we would have understood this if it was the first section of the book. But we're going in order, and we finally have gotten to it. Buoyancy. We all have experienced buoyancy. We've all seen buoyancy, maybe, unless we just haven't been around water at all. This is a very old kind of thing that's been understood for thousands of years. In fact, Archimedes' principle goes back surprisingly to Archimedes, who was an ancient Greek. And Archimedes noticed that when a body is completely or partially immersed in a fluid, the fluid exerts an upward force on the body that's equal to the weight of the fluid displaced by the body. So I've got this Walmart above ground pool, in the backyard because it's summer as I'm making this video. So if I were to, hold my breath and go beneath the water, first of all, you'd be able to tell what volume I displaced if you had a kind of measurements on the side of the pool. The amount of volume that the water went up would tell you how much volume I had. It's a clever way to measure the volume of a complex object like me. It's just by put me in water and see how much the volume of the pool increases, and you know what my volume is, by displacement. By the way, that's not in this section of the chapter. But anyway, if you wanted to figure out basically what the buoyancy on me was, you've seen a crime show where they kind of do a chalk outline of the body. If you could do a three-dimensional chalk outline of me in the water, which is basically what the volume, displaced is, the weight of the water I've displaced, it tells you what the buoyancy, the upward force of that water is. Basically, if the density of the water is higher than mine, I'm going to float. And if the density of the water is lower than me, then I'm going to sink. Salt water, for example, has a very high density compared to a human body. I've been to the Dead Sea, also called the Salt Sea, and you can lay, on top of the Salt Sea like you're laying on the floor. It's very hard to sink in the Salt Sea because the density of the salt water is much higher than the density of say, my body. Anyway, so when a body is completely or partially immersed in some fluid, that fluid is going to exert an upward force equal to the weight of the fluid that you've displaced, with that body. And it's going to, that force is going to exert that force as if it is going through the center of gravity of the fluid displaced. Not the center of gravity of the body in the water, but the center of gravity of the fluid that would have been there if the body wasn't there. So there you have it. We call this, surprisingly, the buoyant force. It's the force of buoyancy that is basically the weight of the displaced fluid. By the way, hydrometer, again, everyday stuff in this section. Hydrometer you might use, in a car to measure antifreeze or something. It's often a dropper that you know what the volume of the dropper is, and the measuring thing in the middle is calibrated, to the volume of it and its particular density, so that when you draw, the antifreeze into it, the density of the antifreeze by how high the gauge goes in the hydrometer. So again, using this Archimedes principle to figure out whether you need to put more antifreeze in your car in the winter and so forth. Okay, this section also treats surface tension. Again, a fairly everyday experience. You've maybe seen a small bug walk across water, the surface of water. How do they do that? Or maybe you've seen that a paperclip can rest on water. What's going on there? Well, basically the surface of a liquid behaves somewhat like a membrane under tension. And the reason for this is, in the middle of a volume of water, the molecules are attracted in all directions. But at the surface, they're being pulled more in the surface direction. So they're not being pulled up. So all that attractive force can be focused on the molecules next to them, and it functions a little bit like a stretched membrane. Or to throw in a little math here, Think of a raindrop. The surface area of a sphere, the ratio of the surface area of a sphere to volume is basically the surface area is 4 pi r squared, and the volume of a sphere is 4/3 pi r cubed. So what's the ratio? It's 3 over the radius. And so the smaller the radius of, say, a raindrop, the bigger the tension is going to be. That's why raindrops are spherical. But if you were to drop a pool of water, out on somebody, there wouldn't be any surface tension because the R of it would be too big. So surface tension is because the attractive forces of the molecules are more focused on the molecules next to them rather than being evenly distributed all around. And there you have the section. It's a fairly easy section with some pretty common sense, everyday kinds of things.